Hello everyone, it is July 17th, 2022, time is 15:45, CDT out. It is Geo-Rant time, Geo-Rant number 171. We will be talking about compositional phase diagrams, specifically for the Feldspars. Whew, sorry, I've been cleaning and stuff too, and this is like my 50th take doing this. If I stumble, I apologize. I just roll with it. I'll try to correct myself as I go, because you know I do these in one take. But it might be 50 takes before you see the final product. Anyway, before I digress too much, we are going to be talking about this triangular diagram here, which I drew freehand, so I'm sorry it looks more like my face than an actual triangle. And it's an equilateral triangle, often used for ternary plots, and this is kind of a ternary plot, not really. It's not really used for that. It's basically a conceptual ternary plot. We'll get into all this later, but first I want to talk about what you see here. First of all, anything in blue is Plagioclase, anything in pink or red, I don't know how it looks on the camera to you, but it's pink, is K-spar or alkali, Feldspar. You see calcium down here with the chemical formula, and here it says calcitic Feldspar. Here you see sodium with the albite formula, sodic Feldspar, and here you see K-spar, potassic Feldspar, you see K, potassic Feldspar, and the chemical formula for that. Just to let you know, I put potassic Feldspar, sodic Feldspar, and calcic Feldspar here because they do appear in literature from time to time, even though we basically don't use them anymore. But if you're looking at stuff even 30 years old, you know, we're talking, 1990s here, you might run across it. So just be aware of it. Here you can see this multi-phase part here, this gap, all right? Now, that's an area where things become homogeneous and can exist as multiple phases, so we discard that because it's too complicated. And you can see here, these are the minerals that form, and they're lying like this. Well, why are they like this? First of all, we'll come back to this later, okay? All right, you can see, first you can see monoclinic. These are crystal systems. That's the M. T is triclinic. You will see all plagioclases are triclinic. However, K-spars are both monoclinic and triclinic. And you see orthoclase and microcline here. This is an end member. This is the very end member of K-spar. The only difference between the two is they have the same chemical formula. The only difference between the two is one's monoclinic and one's triclinic. They form two different crystal systems, hence they're two different minerals. All right. You'll see down here, you see anorthite. This is end member of plagioclase, where you basically have your group 1 or group 2 elements are all calcium. That's why that's here, and there's your chemical formula below. And as a melt cools, now remember, melts are not minerals, so we'll just say felsic melt, but that'll be cooling into a granite or some sort of granitoid. All right. Following Bowen's reaction series, this is a continuous series. All right, this models that. You guys have heard me talk about Bowen's before, so I'm not going to talk about it here. But as that melt cools, often calcium becomes replaced with sodium, and in this direction. So here you have 100% calcium, 90, 70, 50, 30, 10, and 0. And you can see the minerals change as well, and eventually going to the opposite end, albite, which is the other end member of plagioclase. It's considered plagioclase, not K-spar. As you can see, there's not a lot of K-spar minerals. There's a lot more plagioclase ones because these primarily are more common and they're more abundant and they're more distinct and they're easier to identify than these are in particular. Now, so you get to the sodium here. And at this point, sodium has replaced all of your calcium. As you can see, this part is consistent. You always have aluminum, silicon, and oxygen. How they bond to each other changes with the amount of, whatever metal you're using there. And these are group 1, and this is the only group 2. We know this happens, by the way, because of Tuttle and Bowen. We melt rocks and see how this happens. Now, if your melt continues to cool and it has a lot of potassium in it, because if you don't have any sodium or potassium in your magma, you're not going to get any albite, and you're not going to get any orthoclase or monocline. Just physically can't because those elements aren't there. And we'll come back to that when we come to back to this. I want to talk a little bit about this, and I'll get to that later. So if you have potassium in there, the sodium starts to get replaced. And eventually, if that goes on long enough, you will get orthoclase and microcline, or microcline. All right, and there's your chemical formula there. These are more complicated because, you know, you're slowly, you know, you have both calcium and sodium. And here you have both calcium and sodium, and here you only have, oh no, sorry, and here you have sodium and potassium, until you get all the way to here where you just have potassium and no sodium. Now, sanidine is a high temperature forming K-spar. It will actually crystallize when some of these are still crystallizing. So that sometimes that'll be in a rock. You need special circumstances for that, though. They're not really unique. They're just not very common, but they're not rare either. And orthoclase is usually the K-spar you're going to have, or you're going to have one of these two, orthoclase or microcline. Now, plagioclases, and you guys have heard me talk about this before, and I actually have released a second edition of this book. I added some stuff and added some new charts, updates, got rid of outdated stuff. In there, I talk about how you can differentiate under hand lens between plagioclase and feldspars. And be careful; these can be white like quartz. You gotta look. You gotta be able to just take that quartz out and know what that looks like. We're not going to talk about that here, but quartz never forms striations. So if you see striations, you know you have a feldspar. What are striations? Well, it's due to twinning of the minerals, and a lot of times this is your crystal. You'll see those striations are parallel, you have a plagioclase. K-spars generally have no striations except microcline. Now microcline, because it has unique twinning properties, because it's triclinic, like all of these, see, plagioclase is all triclinic, your K-spars are a mix, you know, triclinic, monoclinic, monoclinic. But if you get a triclinic microcline, like plagioclase, you'll get striations, but you'll get them perpendicular. So that's how you can tell. Color can generally be used, but I wouldn't do it. Color is not, you know, conducive for mineral identification. Now, when you're down here, and northite doesn't really do this as that much, but bitonite, and labradorite will. This is a labradorite clock I have. It's actual cut and polished labradorite. Here's the back. As you can see, hopefully you can see in the light here, it's doing it. It's iridescent. That is a intrinsic property of these two minerals, and to this one to a lesser degree. But once your calcium is less than 50%, like andesite, agoclase, and albite, that no longer occurs. That property is gone. So if you see a mineral with just parallel striations that iridesces like this does, you know you have one of these three. And if it's bluish like this, it's probably labradorite. Bitonite and anorthite tend to be whiter. Bitonite can be a little gray sometimes. Like I said, you know, I just got done saying color's not conducive, but they can be used as a guide. But don't get me wrong, you can have grayish anorthite and anorthite. All right, so that's how this works, essentially. And I just wanted to illustrate, this is basically a grandiose illustration of Bowen's reaction series to show you how that calcium can be replaced by sodium. And then if you still have the right chemistry, that sodium can get replaced by potassium, and you can end up with this. Now, we don't really see pure rocks of orthoclase or microcline, of that pure K-spar, but we do see rocks of nearly pure plagioclase. And I need to talk about this here because this will confuse you if you don't know. Oh, by the way, this book has also been updated. This is the updated version. I ordered it, second edition. Here I have a different chart. I don't know if you can see that, but a different diagram of this. But this is in here. It's also in the individual rock, or it's in the individual igneous lab book that can be sold if you don't want to spend $60. You can buy it separately, and it has a red cover on it. Let's see if I can find it real quick before I digress too much here. But yeah, that, all right? So, you can have rocks that are almost all plagioclase. Now, they're common in the deep past, Archean, that kind of thing. And they're called anorthosites, okay? These anorthosites are usually more than 90% plagioclase. And the only other thing that probably would be in them is quartz. And we don't really get them anymore. And on Earth, they only exist as plutons. They only exist as phaneritic or coarse-grained rocks. Bela, you can't get up there. Or coarse-grained igneous rocks, coarse crystalline. We know of no extrusive fine-grained or aphanitic version. You guys have heard me talk about that. Our plutonic crystalline rocks like granite has a fine version, rhyolite, gabbros is basalt, gabbros are coarse-grained, basalt's fine-grained, etc. Anorthosite on Earth, the rock, anorthosite, this is the rock, has no extrusive fine-grained form. We've never seen it. The moon, I think, does have some, or we suspect it to, but on Earth, the conditions have never been right, or they're eroded, it's gone, for that fine-grained to form. Anorthite is a mineral. Anorthite, and this is also a mineral, and this is also a rock. Anorthite is this. It's this plagioclase. But an anorthosite doesn't have to be made strictly of anorthite. These two, anorthosite is not the rock version of pure anorthite. Anorthite could have all of these in here and none of these, as long as it's 90% this. All right? That's a misconception, and that's kind of where things get a little muddy, but we use these terms, I use these terms, everyone uses these terms, so I thought I'd clarify. And same thing with this. See andesine here? An andesite. Andesine's a mineral, andesite's a rock. Andesite can contain andesine, and andesite is a aphanitic or fine-grained extrusive rock. It's intermediate. It's between felsic and mafic. Can it have andesine in it? Of course it can. But it can have a lot of other things in it as well. I can even have some of this. So you got to be careful when you see these words. If you see, and of course, anorthite has an IT on it, as does anorthosite, but andesine is an INE and this is an ITE. So these two, if you can memorize it, you know this is the mineral, this is the rock. This one you just got to memorize, and I know it's confusing. I didn't make it. This is how things have evolved over the years and whatnot. So I know this one's a little more technical for you guys. I didn't want to get any deep chemistry or anything like that. So I just wanted to clear this up, and because somebody did ask me, how do plagioclases become K-spars? And you need the right chemistry, the right temperatures. Now, you may be like, well, if calcium is swapped out for sodium, where does that calcium go? It forms other minerals. Because remember, Bowen's reaction series has two sides. It has the continuous series and the discontinuous series, okay? And then there's other things that can hog these up as well, like micas and things like that, which are common and do crystallize out of melts. So they'll get used elsewhere. All right, if they're not, if this doesn't happen. Now, like I said, if you have, a melt that has none of this, you're not going to get any of this. You're only going to get this. If you have a melt that has this, you're only going to get this. You're not going to get any of this. And if you have a melt that only has this, you're not going to get any of this. All right. And temperature plays a part in this. As a rock or melt starts to cool, this starts to occur. We'll just say you have all three. Now, if that temperature, and this happens more with aphanitic, fine-grained, extrusive rocks than it does with plutonic rocks, if that cools quicker because it's closer to the surface, it'll start going through this, and then all of a sudden it cools before it reaches the temperature where K-spar starts to form. So you have the chemistry to potentially make an alkali feldspar type rock but it's cooled too quickly, so that potassium goes to different minerals, and the rest of that sodium will as well. I know we like to think of calcium as being a calcareous, sedimentary rocks, limestones, dolostone, and it is, but it's a key element in igneous rocks as well. So sodium and potassium. Okay, that's it. If you have any questions or comments, please leave below, and I hope you learned something.